Alright, we're on to part 2 here. First page says we're looking to say that I can use the right angle at the intersection of a tangent line and a radius and the symmetry of the radius to solve for missing angles and sides in triangles. That's a mouthful. All we're trying to do is solve for the missing thing in these pictures, which are a bunch of right triangles. And we'll see the same thing down here, and we'll look for angles on the bottom, side lengths on top. So let's go ahead and start out with number 5. Number 5 is an interesting challenge. What we're given in this picture is a triangle, and we know that since we have a line that is tangent to the circle right here, and we have a radius because it goes from the center to the edge, that's a radius, we know that we have a right angle. And that's always true when a radius and a tangent line meet. So that means that this triangle, by definition, must be a right triangle, which means the Pythagorean theorem will work for us. So we can go ahead and calculate the length of this side right here using Pythagorean theorem. So let's do that. We have small side number 1, 4 squared, plus small side number 2, 7.5 squared, and that's going to equal our unknown side, c squared. So if we plug this into our calculators, we get 4 squared plus 7.5 squared, and that is 72.25 equals c squared. And if we take the square root of that, we get 8.5 is equal to c. So this side is 8.5 long. Here's the problem. We actually aren't trying to find the whole length of that side. We are only trying to find this little part. How are we going to figure out what that is if we don't know what that other piece is? Unless, of course, we do. The nice thing about circles is that a radius is a radius is a radius all the way around. So if this radius is 4, this little piece right here that goes from the center to the edge is also going to be 4. Using that, we can say 8.5, the whole, minus the 4, the part, is 4.5, leaving this part right here as 4.5. So that's how we would calculate that missing part of the triangle. I don't believe any of the other problems on this page have that part, but just be aware that that kind of thing can come up sometimes. Skipping down a little bit, let's look at number 7. 6 and 7 are both nice, interesting ones. We're going to take advantage of both right angles and that symmetry of the radius. So in this one here, we are trying to find the angle down here. That is our goal. We know for sure that we have a right triangle because a tangent line and a radius are meeting. So I know that there's a 90-degree angle there. And if this little piece is 35, then this piece right here must be the other thing I need to add up to 90. So 90 minus 35 is 55, making this 55 degrees. That still is not enough information, though, to help me solve for this missing angle. I still only know this one angle in the triangle. The way I can get around that is by remembering that I have a radius and another radius. And if radii are the same length all the time, this is an isosceles triangle. And if this is an isosceles triangle, then I know that this angle is also going to be 55 degrees. And so let's keep going. That still isn't going to help me, though. It doesn't help me figure out this one because I still only have one angle in the big triangle. But let's trace out this little one here. If I have a 55-degree angle and a 55-degree angle, I can figure out what this one must be. I can say 180 minus 55 minus another 55, and that's going to give me 70 degrees. So I know then that this angle up here is 70 degrees. So if I were to clean up my picture for a moment and get rid of all of this stuff that doesn't seem to help me much, clean all of this off. If I have a 70-degree angle here and a 90-degree angle here, and I have this big triangle, and they all add up to 180, I can take my 180 minus my 90 degree minus my 70 degree, and I'm going to have only 20 degrees left, which is going to go down here. So this is quite a few steps involved in this problem. I had to use the little piece they gave me, I had to know about the right angle, I had to use the fact this is an isosceles triangle formed by the radii, calculate that 70-degree angle, and then finally get to the 20. So a lot of steps involved in some of these angle ones. Last ones down here, I'm just going to remind you that when you're finding perimeter, you're finding this segment and this segment, and you're wondering about the relationship. For one, you can look at the picture and say, man, they sure look equal. It sure looks like I'm staring at a kite. And you are. Whenever you have the radius here as being equal and you have 90-degree angles here, and this is a shared side, we prove that these two triangles are the same by HL. So whenever you see this situation going on, you will know for sure that these two pieces are equal. You can just set them equal to one another.